So, while people are still walking in, we might as well do something a little bit chaotic. We're going to do a Friday hug. Who is not familiar with what a Friday hug is? Okay, you'll... You're lying, I see it. A Friday hug is where you stand with your arms like wide, like you're about to approach someone and give them a big hug. You are all facing me while you do that, and we'll have a photographer here and a photographer here who will take a picture of it. Where's my photographer here? There's my photographer here. Okay, so we're all getting up, doing, yeah? With getting up, I mean stand up, yeah? I know it was just lunch, but hey. Yeah, 1, 2, 3, hugging. Thank you so much. As you're coming in still, I want to remind you that if you want to do a lightning talk tomorrow, you have to sign up before midnight today. You do that by sending an email to the Gmail address that was up earlier. If you don't remember, come and ask me later. Or maybe we can tweet it out once more. We don't have that many yet, so there's still a good chance that you get in. Also, for the location pitches, we only have one location pitched so far. I mean, we can do better than that. Again, until midnight, send us the city that you would like to host the next EuRuKo in. Not just that you want to go there, but you have to actually organize it, yeah? And send the slide deck. Tell the people to stop talking, yeah. That's a lot. Easier said than done. All right, I'm gonna go all flight attendant on you. There is flyers in your goodie bags that tell you about the 2 beautiful challenges that Meister Labs is doing. So one of them is a coding challenge, and you can win actual cash. That's kind of nice. And the other one is that you make a mind map of one of the talks that is about to come up, and you share them with them, and you get a free T-shirt. There's another, it's not a challenge, it's another like sponsor thing. GitHub has their booth upstairs, and they are looking for people to interview about their open source projects. So if you have ever open sourced something and you want to share it with the rest of the world, they will do like audio recording, not video recording, so you don't have to like interview, but it would be really nice to share your stories of open source. All right. As you're not silent with me, I hope that you're silent with our next speaker. Hi, Damir is a software engineer who loves teaching. He's also a remote worker, as I guess so many of us. And he will try to get to the bottom of a performance issue with us, and it's based on a true story, so that's exciting. Damir?
Well, thank you all. Hope you have all enjoyed your lunch. My name is Damir, and today I want to show you a set of tools that I believe should be a part of every developer's, every debugger's tool belt. But before we start, let me introduce you to Midori. Midori is my per debugging partner. She pairs, I program, or debug. And we've been per debugging for quite a while, and naturally, she has heard a lot of horror stories, true horrors, and she has seen some of them, like mismatched parentheses. That's, pretty bad, but there are worse things than that. For example, bad bugs, those that keep you up at night, those that wake you up, that destroy your production server, destroy your production database when you don't have a backup, but we will not speak about those. There are also bugs that are not so bad in the grand scheme of things. They make you a bit embarrassed that you made them. You didn't do all due diligence, but you know, no one is hurt, everything is well, we can move forward. There are also bugs that are very loud. You know, like you call a method on nil, and it looks like everything has exploded, but it's fine. You know, it tells you where you need to look at to fix the problem. And that's okay. There are also silent bugs. They are worse, right? Because they do their damage over time. They don't tell you they are there, and you get to know that only when it is really, really late, when things have already got pretty bad. So this will be a story of a hunt for one such bug. And I like to call this story 2016, a debugging odyssey. So this odyssey begins with my CTO coming to a team channel and asking us to look at a problem that has somehow caused our specs to start running tremendously slow. So, sorry, specs are not tremendously slow, but it takes tremendous huge amount of time for them to start at all. So that's not great, you know, it's slowing down specs obviously as well. And if we can fix that, then we will save hours and tons of nerves for everyone every day. And you know, every debugging story, be it walk in a park or just an odyssey, begins with trying to reproduce the problem, being able to see it by yourself. So naturally, I just start my application, I try to run tests, and they start quickly. I'm using Spring, so naturally, you know, Rails application sits in memory. You start tests, Rails application forks to another process, which is very quick typically, and tests start. So that's fine. And I can't just go to my CTO and say, well, there's no bug, you're crazy, because I know he's not. So I try again. And yeah, still pretty quick. I try to change some code, try again, and there is something, you know, something's happening. So I basically just go with a go to 10, as would a basic programmer say, and continue this loop. Modify some code, start tests, and see if there's something else. And after 6 or 7 attempts, suddenly it takes about 20 to 30 seconds for Rails application to fork and for tests to start. So, okay, my CTO is not crazy, there is definitely something there, and I feel a rush of adrenaline because I solved something, I reproduced the issue. There is something to fix. So yeah, that's great. But what did actually introduce the issue? Where did it come from? Because if I try the same steps on a small Rails application, there's no problem there. Like, it runs very quickly. So I want to find us one commit that introduced the issue into the code base and understand then how it happened. So I reached for one of my favorite tools for that, Git bisect. Git bisect uses the magic of binary search to quickly, in a very small number of steps, identify a problematic commit. So I start the issue. All I need to do is tell Git where the bug is and where I'm sure that there is no bug. So I mark one commit as bad and mark the other commit as good. So let now Git do its job. Git will check out the commit in the middle between those two, in this case this EE, and will ask me to tell it whether it's good or bad. So I run tests, I see that commit is bad, so Git marks it as such, and we know automatically that all commits that follow EE are also bad. So Git repeats now, it selects another middle commit, it asks me for status, it builds fine, so all commits before that are fine as well. And now we just have this final commit to test for, and we will know where the problem is. So, you know, I'll leave you with a cliffhanger. But the problem with Git bisect is that you know which commit was good, so you have to identify that first. But because bisect is using binary search, we don't have to care that much, right? Because to identify one bad commit among thousands of them, we just need 13 steps. So we can just take something written centuries ago and rely on Git to do the magic. So that's what I try to do. So I write a small script that will tell me, is the issue present in this commit or not? Are tests getting slower and slower to start? And I go to sleep, I wake up, I run the script, go to sleep, wake up in the morning, have a cup of coffee, and eagerly look into the results of the script, and I find that script has crashed. Of course it did. Why? Well, I went long enough back into the history that I don't have gems installed that I had a long time ago. So I had to install gems as I'm checking out old versions of the code base. Yeah, fine, normally. OK, so I add a line bundle install to the script. I let Git do another job. I go to bed. I'm very excited. I twist and turn. And in the morning, it is, well, of course, another crash. Why? Oh, I forgot about the database. Code and database also go out of sync as you check out all the commits. So yeah, OK. Rake db reset, whatever. Let's go to sleep, or maybe not, maybe just stay awake, it will be quicker. Because, well, it will crash again, right? That's debugging. Why? Well, funny story, really. There was this guy, he introduced a dependency into our primary product onto his private repository on GitHub. Sometimes we do things like that, yeah? And eventually, that dependency wasn't necessary anymore. We removed it from gem file. He cleaned up his Git repository, removed the repo. But now there is a hardline. I cannot check out the previous code and make it work. So there is a lesson here expressed in words of great General Maximus. What we commit in life echoes in eternity. So try to always aim for making every commit to be stable, to be able so that you can check it out in future and run your application or your tests against it. One other debugging problem is that issue was getting more and more pronounced with time. So when we got closer to the source, it was becoming harder to identify the signal versus the noise. But somehow we got around it, and I got an indication about where the problem finally could be. And as you could guess from the picture behind me, it's in Monolith. Well, Monolith is actually, or was, a framework that we built internally to help us write monolithic Rails application. Actually, it would allow us to mount classes, units of business logic, directly onto Rails' routes. So it would encapsulate controller logic and some operations together, and it would work its magic. It is actually pretty nice to work with. But that is not a commit of 100 lines of code that I hoped I would find. I just found one merge commit that introduces a whole new technology, changes tens of thousands of code. So finding what probably introduced it doesn't really help me too much. But what helped me was to know that if this was an issue, it explains why it was getting worse and worse with time, because we were gradually adopting it, right? So we can assume for now that it has something to do with this new framework, with this new technology, but it doesn't help us fix anything. So I was discussing this with people, pair programming, rubber duck debugging, Midori debugging, and a lot of people ask me, is it maybe a memory leak? That could explain something. So there is a naive approach to test for memory leaks. One is just to look at the memory footprint of your application, the memory profile. So if it is wibbly wobbly, but always returns to some baseline, well, we can assume that there is no memory leak. But if your memory profile reminds you of Usain Bolt, then we are pretty confident there is a memory leak. Things are not so easy in Ruby land. That's why I called it naive approach, right? Because Ruby takes memory as it allocates it, but it doesn't give it back to the operating system. I mean, it does, but very, very slowly. So memory profile of most Ruby applications will look like this. They will allocate memory, but only slowly release it to memory system. So eventually there is some top line, and just memory doesn't go much below that. And we call that memory bloat. Memory bloat is not bad. It's just Ruby process that took a lot of memory. But there's nothing in that memory, so Ruby is not really concerned too much with it. So we have to actually look for what is in the memory. And if we can find what is in memory and how long it has been there, then we can say if there is a memory leak or not. And Ruby, luckily, provides two very easy methods to help us do that. So they sit in object space. One of them is trace object allocation starts, which basically just starts collecting information about what should be in memory, what Ruby allocates. And the other line is dump all, which will take everything that is in Ruby's dynamic memory, in heap memory, and dump it to a single file. And that file will contain many lines. Every single line will be a JSON object that you can easily inspect. There are many interesting attributes, but for now I really want to focus on this one, generation. Generation means what is the garbage collector generation in which this object was initialized. It tells us how old the object is in the memory. And it's really hard to see something in this file because it has, just for this example of printing hello world, we have more than 20,000 objects generated in heap. So, good luck just scrolling through it. But we have tools. We have tools like heapy. Heapy is a really nice tool that gets you a condensed summary of what is in there. Basically, it gives you a demographic statistics. Well, you have 15 objects that have been allocated in the 11th garbage collector generation, and 20,000 have been generated before we started tracing, so you don't probably care about them. And this is just for a simple program, so we had only one GC generation, but typically we would have many of them, and we could inspect every one of them individually and see where those objects actually got created. So in this example, this is a separate example, obviously, because we have much more objects and more generations. We have the most objects being generated in the timeout RB. So that can potentially give you something. So I was exploring this heapy report for my application, and I noticed that I have really, really many class DSL objects. So I'm having a hard time to interpret that. I just don't understand what could it mean. Like, why would I have so many class DSL objects? So I just mark this as plausible theory. There could be a memory leak, but let's keep exploring. So I've been kind of going around. I've looked for what introduced the problem. I looked at the memory profile, but I didn't actually look at why it was slow. What was being slow? Was there one method that was running longer than necessary? So there was another approach I could try. I could just take a look at how call stack changes through time, tracing call stack. So let me just quickly explain what I mean by looking at this simple program. So basically we have main method calls two other methods, and main calls say hello and say bye. Say hello calls two other methods. We don't care about them. I just remove them here for brevity reasons. But when we start running this program, this is what call stack actually looks like. We have main method on the bottom, which means it's calling methods on top of it, right? It's on the bottom of the call stack. It calls say hello, so say hello is above it. Say hello calls read name, and read name would be on top of the call stack. And this is some time instance 0, right? T0. So in next time instance, next CPU cycle, we call method greeting from say hello. And now we represent that in the call stack as well. So in next time instance, we move from say hello to say bye, and now our call stack will represent that. But as we were going this, we were keeping all previous versions of the call stack on this image, so that we can easily see how the call stack was changing through time. And what we can see here is that main is the widest block, so that means it was also the longest time on the call stack. And so the wider a bar is, the longer it is on the call stack, which means that longer that method has been running. So longer means worse. More probably. I mean, everything on the bottom will be long, of course, but if there is something very long on top, that will be an indication for us. So this visualization, this call stack trace is actually called a flame graph. And we can render flame graphs very easily with Ruby. There is a gem called flame graph. You install it, and you can just invoke one method on it, and it will render an SVG file for you that has all these nice shapes, bars that you can inspect, what method is which, and how long it has been running. Okay, so great. Let's just put flame graph somewhere in the Rails application initialization, and we'll see something. So I do that. I generate SVG. I double click on it. It opens in Chrome. That was my default browser 3 years ago. And I don't see a picture, I see browser crashing. I mean, you can just imagine how many methods are called in the Rails application startup initialization process that browser simply couldn't render it. Funnily enough, Safari handled it, and since then I'm using Safari as my primary browser. And this is what flamegraph was rendering like. So looking at just one flamegraph is really hard. You don't have a feeling for units of measure unless you know what you're looking for. I mean, if you know that you can look for peaks, vertical peaks as well, because that means there are lots of methods calling one another. There's a lot of on call stack, but that doesn't necessarily always imply slowness. So, and because my application was getting slower through time, all I had to do was render 3 or more flamegraphs and compare them. Luckily, Safari handled 3 SVGs with flamegraphs open in 3 different tabs. I was really impressed with the browser at this point. So in my first tab, I have a very simplified flamegraph that looks something like this, and it seems okay. But then I quickly switch to another tab, and it changes. Something there changes. Then I switch to the third tab, and it changes again. So at this point, I think it's really obvious that there is one method that's simply taking more time than in third attempt, in third iteration, than it was in first 2. So great, I finally found something. I found the source of the slowness. Let's now fix this method. And of course, this method belongs to Rails. So yeah, good luck with that. It's Rails bug, let me report. No, of course not. I mean, it is a method in Rails, and all above, you don't actually see in the flamegraph because there are now methods written in Ruby and in C. But let's not care much about Ruby. Hopefully, Ruby is not slow, is it? So let's first look at Rails. And obviously, it's not really just Rails' problem because empty Rails application is not slow, so it must also be something from us. So that one long block was actually a method that is sitting in action pack, lib, action dispatch, routing, route set. And the method was called clear. This is slightly simplified listing of that method. And I want you to focus on these 6 lines. What we have here are 2 loops. One is iterate, both of them are iterate through some enumerable that presumably contains method names. Both of them are added to this block argument helper. And then those methods are removed from some module. They wait undef method. So let's see actually what those modules are. And those modules, after some further inspection, I realized are modules that contain methods that Rails generates for us to generate URLs or paths that we use in our code base, in our controllers, or in our views. Basically, path helpers contains all methods that generate paths, and URL helpers contains all methods that generate URLs. And basically what happens whenever you change code in Rails, and whether you are in development environment or starting the application with Spring, when there is a long living Rails process, you change the code, Rails will have to reload routes files. And when it reloads routes files, it has to reload also these 2 modules. So it will go through every method from each of those 2 modules and remove all methods from them, and then add those methods again. It happens in a different place. So now I'm getting somewhere. It's actually removing a method from a module slow in Ruby. So I decide to do a small benchmark. I create a small script. It creates tens of thousands of objects. It creates one module, includes that module into those tens of thousands of objects, and then adds thousands of methods and removes thousands of methods. So normally, I would expect some linear time because I'm just removing methods from one module and adding them back there. So I'm hoping for constant time. We could also expect maybe linear time because we are increasing the number of objects, right? So that has to mean something. But what happens in Ruby is unfortunately this. I don't want to even try to guess which function this is, and it's not really important, but obviously it's slow. It's slower than we expect. So, problem is not in Rails. Let's go deeper. Let's dig deeper. Let's dig into Ruby. And in VM method C, that is. Yeah, nice little C code for after lunch, right? Let's zoom in a bit. So this is a more important part, but actually let's just focus on this one line here that shows us that whenever Ruby undefines a method from a class for a module, it actually defines that method again, but with this marker undefined, undef. So we actually define those methods. Ruby internally defines those methods, tells Ruby process not to look for them here again, that they don't exist, and hopefully everything will be okay. So if this is a slow part of removing a method, the question is adding a method to Ruby slow? And yes, I guess it is. Half of the time of adding a method is actually spent clearing method cache on all objects in the Ruby. So potentially there is an improvement there, but this is situation currently. So if you have one module included in a bunch of controllers, or if you have a bunch of objects that you want to remove single method from, well, you have to keep in mind it's not fast. It's not terribly slow, but it will probably be a bottleneck for you, but you know, just in case. So yeah, now we finally know what is slow, and we are getting to the bottom of this. But, okay, but not yet. How is actually our application affecting Ruby to show off that slowness, to present it to us? So let's just see what we already know. Git bisect told us that we introduced this whole new framework that actually mounts objects onto Rails' routes. Heapy told us that we are maybe leaking memory, and objects that we are leaking could be classes, maybe because we are leaking a lot of class DSL objects. And flamegraph told us that what is slow is the fact that we have so many controllers that it is slow to remove methods from them. So if we now look at the monolith, this library, and how it works, you would see that to mount an object into Rails route, it actually has to generate controller for Rails to follow Rails' routing. And so could that be a problem? Could it be that our app is actually leaking controllers? So, well, yes, it is the case. Our app was generating anonymous controllers, and it was generating them eagerly, which means every time routes RB was parsed, we would generate a new controller, we would mount it onto a route, and that controller would be delegating work to our business logic objects. And that wasn't great, so, but now we know what to do. So we finally found the source, and all we have to do is fix it. So how do we fix something that is slow because it's very eager? Well, we make it lazy. So whenever a route is requested, we actually just go and only then generate a controller. And if you remember, I was speaking about Spring earlier, and that the problem was that our master Rails process was getting bigger and bigger. So it was slower and slower to reload routes from it, and only then it would fork. But with making this lazy, we're actually keeping that process as is. We fork, only then we actually create those controllers, so we don't actually care if they are leaking or not anymore, because that process lives quickly. So that was a success. We could actually now go forward and run tests very easily. So what is actually to take away from here? What is the lesson? Well, in my opinion, the lesson here is that when debugging, you need to know your application. And your application is not just the code that you wrote. It's not just code that your team wrote. It's also code that you imported into your application. It's your library. It's your framework. It's all of your gems. It's your programming language as well. So when you're debugging, you need to be ready to go wide with your assumptions. You need to assume that everything or anything can be broken. And you also need to go very deep when you're doing a research, because you never know on what levels things are actually broken. and how it affects abstractions further on. So go wide, do a deep research, and choose your dependencies carefully because they can really make or break your application. Thank you very much. I will be around both days, and if you have any cool debugging stories that you would like to share for me, please tell me. I will report them back to Midori. She will be happy to hear them. And sadly, we don't have any time for Q&A. Thank you very much.
Thank you, thank you. There's no Q&A. You've been told. So, you know. That was harsh. Thank you so much. I've been told that you people should be told that please do not use those doors on the side if you want to get out, but use the doors in the back, because the sponsors are there and it's kind of loud and then it interrupts the talk and nobody wants that. So please don't use the doors there if you want to go out, if you want to go to the bathroom, use the doors in the back. Good. That being said, we're going to